Today, our first objective is to understand why regularization is necessary in the learning process, especially in the evaluative context. We recall that overfitting or overfitted models is a phenomenon we aim to avoid. Thus, to combat overfitting, regularization serves as a powerful tool. Overfitted models exhibit excessive complexity and overly steep curves, which are often manifested through large weight values in the model. Regularization is specifically designed to address this issue by penalizing large weights, thereby promoting smoother models with smaller weight magnitudes. Therefore, regularization serves as a crucial aid in the battle against overfitting. Now, let's explore regularization in practical environments, where we understand how it can be implemented using specialized libraries, such as L1 and L2 regularization. To illustrate this, we'll create a simple dependency and visualize it as follows. We'll generate 10 points ranging from -5 to 5 and apply a function to them. Representing our green law, we'll then add a small amount of noise to simulate real-world variability. These points constitute our training sample. Next, we'll create a test sample without noise, consisting of 10 objects with one feature each. Finally, we'll visualize all our points together, including both the training and test sets. Here we are creating a pipeline using makePipeline function. The pipeline consists of 2 steps: polynomial feature expansion with degree 11 excluding bias term using polynomial features, and followed by standardization using standard scalar. After creating the pipeline, we fit it to the training data to learn the parameters needed for feature expansion and standardization. Then, we transform both the training and test data using the fitted pipeline. Let's train first L2, ridge regularization, and create a list of regulation coefficients. These are our regularization coefficients from the smallest value to the largest value. Firstly, we will loop through them and initialize the ridge models and train them on training samples. The trained model will be added to the list that we created above, and we will also add model weights to the list that we also created before, so we accumulate models trained on different regulation coefficients, and add weights and coefficients of models also trained on different ones. Since the initial linear regression model is prone to overfitting, we do not add coefficients. To commence, we plot the training and test points precisely on the graph. Subsequently, we generate an additional auxiliary sample comprising 100 objects to achieve smoother visualized curves. By increasing the number of objects, we enhance the smoothness of the visualization. Finally, we iterate through all models to make predictions on the transformed new data and plot them. Additionally, we plot a line graph representing the most overfitted model, linear regression, which we've included in our list of models, depicted with a blue line. We observe that the linear regression model without any form of regularization demonstrates the most pronounced overfitting, as it closely fits almost every training point, resulting in very large weights and slope coefficients. With the introduction of regularization coefficients and training the ridge regression L2 implementation, these weights decrease gradually, as indicated by the blue line. Moreover, when the regularization factor becomes excessively large, our line tends to remain linear. Next, we assess the quality of these models to evaluate their performance. For this purpose, we create a data frame. When there is no regularization, our metric on training data appears ideal, but on test data, it displays significant negativity, which we aim to mitigate using the regularization coefficient. As the regularization factor decreases, the effect on the training metric diminishes while it increases on the test metric. Further increasing the regularization coefficient results in a slight decline in the training metric and a gradual rise in the test metric. Let's also visualize the weights with you, and we go through this array in the list and visualize it through a linear graph. If we penalize the model more, the weight starts to decrease well, and in the end, of course, they become something very similar to 0. This is our ridge regulation L2 regularization. Further, let's generate our regularization coefficients for L1 Lasso regularization. Now we proceed to train our Lasso regularization models on the training samples and store their coefficients and models. Simultaneously, we train the most overfitted model using linear regression. Upon completing these steps, we visualize our models on the graph, We represent the overfitted model as a blue line using linear regression. Subsequently, we observe our less overfitted model, depicted by a straight line indicating a highly penalized model. Furthermore, we calculate metrics for the models and compare them. Initially, without any regularization coefficient, the metrics indicate favorable results on the training sample but poorer results on the test sample. Thus, we introduce regularization to our models. Notably, training the model with a small regularization coefficient induces metric changes for both the training and test datasets. Let's visualize our weights again and see that when the regulation coefficient is small, it is worthwhile to increase the regulation coefficient as our weights start to decrease, and here all the way to 0. An interesting feature of L1 regularization is that it can act as a feature selection. With Lasso regularization, the weights associated with certain features may become 0, indicating that these features are considered irrelevant by the model. Consequently, we can remove these features from the training process, reducing complexity and potentially improving performance. Additionally, we have ElasticNet regularization, which combines both L1 Lasso and L2 Ridge regularization techniques, striking a balance between feature selection and regularization. It enables us to leverage the advantages of both methods. In ElasticNet, we introduce two regularization coefficients alpha and L1 ratio. The alpha coefficient determines the overall strength of regularization, while the L1 ratio controls the balance between L1 and L2 regularization. For example, setting L1 ratio to 0 results in no L1 regularization, applying only L2 regularization, whereas setting L1 ratio to 1 leads to no L2 regularization, applying solely L1 regularization. We can experiment with different values of alpha and L1 ratio to identify the optimal combination for our model. Furthermore, we can adjust other parameters such as the number of iterations and include a well-trained model without any regularization for comparison. Finally, we visualize the predictions made by these models to assess their performance and determine the most suitable regularization approach for our specific problem. Today we learned about regularization and its importance in machine learning. Thanks for watching. Wishing you the best of luck with your machine learning endeavors. Goodbye, everybody.